There are tools sitting in estate sale bins right now that a 22-year-old mechanic will pick up, turn over in his hands 3 times, and set back down without knowing what it is or what it did. Not because he is unintelligent, because no one showed him. These tools did not disappear because something better came along. Most of them disappeared because the knowledge that made them work stopped being handed down. We are going to look at 10 of them today. What they were, how they worked, and what we lost when they stopped being used. Number 10 is the one sitting in a coffee can in your grandfather's garage right now that you probably thought was trash. Number 10, the taper reamer. A 6-inch steel shaft with a tapered fluted body, a wooden handle, and no moving parts whatsoever. It looked like a screw that had given up halfway through. A young mechanic today would guess it was some kind of punch. It was not. The taper reamer was used to bring a drilled hole to an exact diameter by hand, removing material slowly and precisely with each rotation. When a bolt hole was slightly off, when a bearing seat was tight by 0.005 of an inch, or when a hand-drilled hole needed to be brought to a clean finish before a taper pin could be seated, the reamer did it. No power required, no machine required. The hand controlled the pressure and the angle. The result was a hole that fit the part exactly, not approximately. Modern shops use drill presses and CNC equipment for this. They are faster. They are also $200,000 and the size of a room. The taper reamer fit in a shirt pocket and cost less than $1. One handed the job to the next generation and the generation after that. Most of them are in bins now, priced at 50 cents, going home with people who use them as letter openers. Number 9, the spark plug gap tool. A small flat disc of stamped steel with a dozen graduated blades folded out from the center, each blade a different thickness in thousandths of an inch, each one labeled with a stamped number too small to read without good light. This was the feeler gauge set built specifically for setting spark plug gaps in an era when the driver tuned his own engine and understood why the gap mattered. Too wide and the spark was weak. Too narrow and it misfired under load. The correct gap was specified by the manufacturer and achieved by bending the ground electrode with a small hook tool until the blade of the correct thickness slid through with just the right amount of drag. Not loose, not tight, resistance that felt like pulling a piece of paper through 2 fingers. That sensation was the calibration. The hands learned it after 3 or 4 engines and never forgot it. Today, pre-gapped plugs are sold by the box and installed by a shop. Most drivers have never seen the inside of their engine and could not tell a firing order from a fuel injector. The knowledge that made a man independent from a service department got traded for convenience, and the trade was accepted without much negotiation. Number 8, the valve spring compressor. A C-shaped tool of heavy steel with a threaded screw on one arm and a cupped pad on the other. It looked like a medieval torture device and operated on a principle so old it predates the automobile by several centuries. Compress the spring, and the keepers that locked the valve in place became free. Release the spring, and everything locked back together. This was the tool that let a man do a valve job on a flathead engine on a Saturday morning with no machine shop involved. The engine came apart on the kitchen table if the wife was understanding enough, or more commonly on a workbench over a spread of newspaper. The valves were lapped with compound, the seats were cleaned, and the engine went back together with a compression that matched factory spec. That engine then ran cleanly for another 100,000 miles. Today, a valve job is a machine shop operation billed at an hourly rate that makes a man wince. Not because the work became more complicated, because the knowledge left the garage and went professional, and the tools followed the knowledge out the door. Number 7, the slide hammer. A steel rod 2 feet long with a weighted slug that slid freely along the shaft, a handle at one end, and a threaded tip at the other. The principle was pure physics. Thread the tip into a stuck bearing, a seized bolt, or a dented panel from the inside. grip the handle, drive the weight hard against the stop at the handle end. The inertia traveled down the rod and yanked whatever was threaded to the tip in the direction you needed it to go. A dent puller, a bearing puller, a CV axle extractor, one tool doing the work of three. The man who owned one and knew how to use it could pull a wheel bearing on a gravel driveway with no hydraulic press. The bearing came out through physics and patience instead of machinery and money. Young mechanics today recognize the concept when it is explained. They have simply never held one or learned the feel of the right strike weight. The gap between knowing a principle and being able to apply it with a hand tool is exactly the gap that a generation of garage work used to close. Number 6. The ball joint separator, also called the pickle fork, a forged steel wedge with a split at the narrow end, sized to fit between a ball joint and its housing. You drove it in with a hammer. The taper did the separating. There was no hydraulic press. There was no special adapter kit. There was a wedge and a hammer, and the understanding that a taper driven under force will separate two surfaces that were never meant to separate easily. This tool destroyed the rubber boot on whatever joint it touched, which meant you were committed to replacing the part when you used it. That commitment was the point. You only used the pickle fork when the joint was already bad. You were not preserving anything. You were removing it. Young mechanics are sometimes handed this tool and asked what it is for. Most guess correctly on the general principle. Few have ever actually driven one home with a 3-pound hammer and felt the joint let go. If this kind of content is useful to you, take 2 seconds right now and subscribe. Every week we cover the tools, the methods, and the knowledge that built things to last. Number 5. The thread chaser. Not a tap, a thread chaser. The difference matters. A tap cuts new threads. A thread chaser cleans and restores damaged ones without removing material. It was a specialized tool for a specific problem that showed up constantly in garage work. A bolt hole that had been cross-threaded, stripped slightly at the entrance, or packed with rust and old sealant until the threads were no longer usable without cleaning. The chaser ran into the hole and followed the existing thread form, pushing debris out and reforming the profile without cutting deeper. The hole was saved. The part was saved. The assembly went back together without a helicoil insert and without machining. The chaser required knowing the thread, pitch, and diameter of the hole being chased, which meant knowing how to read a thread gauge, which meant understanding that threads are a specification and not a guess. That chain of knowledge is intact in very few garages today. Most young mechanics reach for the tap and drill the hole out to the next size up. It works. It is also the answer to a different question than the one being asked. Number 4. The timing light with a vacuum advance port checker built into the lead. A stroboscopic lamp powered by the battery clamped to the number 1 spark plug wire triggered to flash at the exact moment that cylinder fired. The light froze the timing mark on the crankshaft pulley in place against the degree scale on the timing cover, allowing a direct reading of ignition timing in degrees before or after top dead center. Then the vacuum hose from the distributor advance was disconnected. The reading changed. The difference between the two readings was the mechanical advance curve, and knowing that curve told you whether the distributor was working correctly and whether the engine was running the timing the manufacturer intended. This was not a mystery. It was a measurement. A man who could time his own engine with a timing light understood why his car ran the way it did. He could diagnose a stumble under acceleration, a flat spot at cruise, or a tendency to ping under load without taking the car anywhere. Today, timing is managed by the engine control module and is not adjustable. That is not a critique, it is a fact. The timing light now lives mostly in tool collections alongside the carburetors it used to serve. Number 3. The oil stone in its wooden case. Not a sharpening stone for kitchen knives, though it did that too. This was a precision lapping stone, finer grit, flatter face, used for seating valve faces, truing gasket surfaces, and bringing machined surfaces back into tolerance when they had warped slightly from heat. A cylinder head gasket surface that had pulled slightly at a corner could be brought back to flat by lapping it on the stone with cutting compound. The work was slow and required checking frequently with a machinist's straight edge across the surface. It was also free. The alternative was a machine shop visit, a surface grind, and a bill. The man who kept a good oil stone and knew how to use it had a capability the machine shop offered for money. He did not need to use it often. When he needed it, it was there, and he knew what he was doing with it. That combination, the right tool, the right knowledge, ready when needed, is what made a home garage capable of work that would today be considered professional. Number 2, the vacuum pump and gauge. A handheld unit, one moving part, a small lever pump connected to a calibrated vacuum gauge. It did two things that a modern scan tool cannot. It tested the function of any vacuum-operated component directly by applying a measured amount of vacuum and watching whether the component held it, and it bench-tested components removed from the vehicle without running the engine at all. An EGR valve, a brake booster, a vacuum advance unit, a heater-controlled door actuator. You applied vacuum, you watched the gauge. The needle held or it fell. If it fell, the component leaked. If it held and the component moved, the component worked. There was no diagnostic code. There was no communication with a module. There was a gauge needle and the understanding of what its behavior meant. Diagnosis by direct measurement instead of by fault code retrieval. Both methods have their place. Most young mechanics today have used only one of them, and it is not the one that works when the battery is dead. Number 1, the machinist's rule with a depth gauge attachment. Not a tape measure, not a caliper. A rigid rule 6 inches long graduated to 64ths of an inch on one side and millimeters on the other, with a sliding depth gauge blade that locked with a small thumb screw. This was the most used measuring tool in any serious garage and the least recognized today. It measured the depth of a counterbore to check for a recessed gasket. It measured the protrusion of a cylinder liner above the block deck. It measured the setback of a valve seat. It measured the gap in a brake drum before turning. Every measurement was direct, readable, and repeatable, without a battery, a digital display, or a calibration certificate. The man who learned to read a rule to 64ths of an inch had a measuring capability that cost him $3 and lasted his entire life. Young mechanics who have only ever used digital calipers are faster. They are also helpless when the battery in the caliper dies at the wrong moment, which is always the wrong moment. 10 tools. None of them required electricity. None of them sent a code to a screen. All of them required the user to understand what was being measured, what was being done, and why. That understanding was the actual tool. The steel and the handles were just the part that made the understanding useful. What we lost when these tools left the garage was not the tools. It was the chain of knowledge that connected one generation of mechanics to the next, passing forward not just the how, but the why. When you know why a thread chaser works differently than a tap, you understand threads. When you understand threads, you understand fits and tolerances. When you understand fits and tolerances, you understand mechanical assembly. That chain does not come from a scan tool. It comes from a cold garage, a set of hand tools, and someone who knew what they were for.